Alright, so today we're going to be talking about how to solve balanced force problems. Uh, we've got two parts to this. In this first part, I'm going to be talking about how to do problems that involve no trigonometry. So from our lab, we know that if forces acting on a system are balanced, then the system travels with a constant velocity. The vice versa also works. We've got that if the system travels with a constant velocity, then the forces acting on that system are balanced. Note that also, being at rest also counts as having a constant velocity. Objects at rest have a velocity of 0, so if you remain at rest, you do have a constant velocity, so keep that in mind as well. So in terms of setting up a solution for a problem, we know that if we have a description of a scenario and we know that the system travels with a constant velocity, that kind of gives us a clue as to how we should draw our force diagrams. For example, if we take a look at the forces in the vertical direction or the y direction, they have to be drawn so that the forces are balanced. Likewise, if we take a look at the forces acting in the horizontal or the x direction, they have to be balanced as well. So what we have here is a way to draw out a force diagram, and likewise we also have a way to write equations for the y direction and the x direction. What this means is that the forces that point upwards have to be equal to the forces that point downwards. Likewise, if we take all the forces that point to the right, they have to be balanced and equal to the forces that point to the left. In order to do these problems, we also need our equation from the force of gravity lab. We have the force of gravity is equal to 9.8 newtons per kilogram times mass. Okay, so to start us off, I'm going to do a few examples. In this first one, we've got a 50 kilogram bucket, and it's raised at a constant velocity using a rope and pulley. What's the tension in the rope? So first, let's identify our system. We're going to use the bucket as our system, and we've got to draw a force diagram now. So we've got our system is the dot. Pulling upwards is the force of tension. On the bucket by the rope, and pulling downwards, we've got the force of gravity on the bucket by the earth. Now, since the problem says that the bucket's traveling at a constant velocity, we're able to say that these two forces are equal to each other. The next step is to try to get some numbers on our force diagram. We know that the force of gravity is related to the object's mass, and we know that it's related by this equation, 9.8 newtons per kilogram. That's the strength of the Earth's gravitational field, is times the mass of the object gives us the force of gravity. So we've got 9.8 times 50 kilograms, and that gives us 490 newtons. Referring back to what the problem wants, we want to know the tension in the rope. So let's write out some equations. We know that in the x direction, looking at our force diagram, we've got nothing going on there. So no equations, it's good. And we've got in the y direction, we've got the force of tension based on our congruency marks has to be equal to the force of gravity. So since we just found out that the force of gravity is 490 newtons, we know that the force of tension also has to be equal to 490 newtons. And we're done here. Okay, for our second and final example, we're going to do something a little bit more complicated. Here we've got a situation where you try to move a 100 kilogram box by pushing it to the left with a force of 200 newtons, the box does not move, and we want to determine the normal force and the force of friction on the box. So I've identified the system as the box, and we're going to draw a force diagram for it. So here's our system. Let's start off with what we know. We know that we're pushing it to the left with a force of 200 newtons. So we've got F sub P on box by U. And if you're an honors student, I may call that normal force, but it doesn't really matter in this case. It's just the force applied by the person. And we also know that since the box has a mass, we have that this is the force of gravity on the box by the earth. Pointing upwards, since the box is on a surface, we know that we've got a normal force pointing upwards. Normal force on the box by the floor. And the box doesn't move, so we know that there has to be something to balance things out in the right direction. So here, that will most likely be the force of static friction. So we've got the force of static friction on the box, also by the floor. Okay, remember, static friction is going to oppose the intended motion. So if you push to the left, friction is going to oppose that, so friction will point to the right. Now, since the box doesn't move at all, we know things have to be balanced. We've got the normal force. The force that points up has to be equal to the force of gravity. And that's where our y equation is going to come in. We know that the normal force is equal to the force of gravity. Obtaining our x equation, we're going to look at all the horizontal forces, and we know that the force applied by the person has to be equal to the force that points to the right, which is the force of friction. So we know F sub P has to be equal to the force of static friction. And those are our equations. Alright, so solving for a few things, we know right off the bat that F sub P is 200 newtons. Okay, if that's 200 newtons, then so is this. And we've already got half of our answer. We know that the force of friction then is 200 newtons. Working in the vertical direction, we have to do just a little bit more. We've got the force of gravity equation. We've got 9.8 newtons per kilogram times the mass of the object, and that gives us 9.8 times 100, and this ends up being 980 newtons. So if that's true, then we know that the normal force has to also be equal to 980 newtons because of our congruency mark, so we've got 980 newtons down here. And that's it. Here's our problem and our solutions, and that's all we have for solving balanced force problems. Part 1, no trigonometry. So check out part 2 when you're ready to work with problems that involve trig. I'll see you in class.